Hello, welcome to this video. So this is a video on the paradoxes in special relativity. So we'll be talking about two paradoxes. One paradox concerning space and therefore length contraction called the barn paradox. And then we'll be looking at another paradox in special relativity which concerns time and time dilation. And when we look at that paradox, we'll also be mentioning why, for the twin paradox, we need to actually bring in a little bit of general relativity. So that's the plan for this video. If you enjoy this video, I would recommend checking out the other videos on the special relativity playlist. But anyway, let's get cracking with the paradoxes in special relativity. So we're going to start with the barn and the pole paradox. And the idea of this is essentially we want to fit a pole inside of a barn. And both the pole and the barn have the same, let's say, horizontal length if we're fitting the pole in the barn horizontally, when they are at rest relative to each other. So if we put the pole next to the barn, and we just leave the two objects as they are, when we measure the length, we'll conclude that they have the same length. Now, it might sound trivial to then be able to fit the pole in the barn. However, relativity shows that if we look at a phenomenon called length contraction and ignore other aspects of relativity, we do seem to be able to create a paradox with this apparently simple setup and this attempt to fit the pole in the barn. So to start off with, there are different versions of this paradox, but I'm going to be working with this one. We have a pole, we have a barn, and when they are at rest relative to each other, they have the same length. However, we then, displace the pole some way from the barn, and by some mechanism, it doesn't really matter how, we have the pole moving relativistically towards the barn. Now, the pole could be moving relativistically because Superman is running with or flying with the pole. It doesn't really matter how the pole is moving relativistically. The point is we have a relativistically moving pole. Now that might sound a bit absurd, but it's within the realms of what is physically possible, so let's run along with this idea. Well, in one reference frame, so for example a reference frame of somebody, let's say, inside the barn, who is clearly at rest relative to the barn, they see the pole moving relativistically. And if we think back to Lorentz transformations, as the pole is moving relativistically, and relativistically towards them, the pole should be length contracted along the direction it is moving. So if the pole is moving along the horizontal axis, the pole should be contracted horizontally. And that will mean that according to somebody who is stationary inside the barn, the pole should have now a length that is shorter than the barn and be able to fit snugly into it. So according to somebody inside the barn, yes, the pole can fit inside the barn. However, if we now jump reference frames, we end up with a seeming contradiction. So when we jump reference frames, we're going to be jumping to a reference frame somebody co-moving, so moving with the pole. So let's say Superman is flying and holding the pole, and both Superman and the pole are moving at the same relativistic velocity relative to somebody in the barn. Well, in this case, according to Superman, the pole is not the thing that is moving, because the pole is stationary relative to Superman. The thing that is actually moving relativistically is the barn. So, in Superman's reference frame, the pole has its original length, but now the barn is length contracted. And if the barn is length contracted but the pole had its original length, then the pole shouldn't be able to fit inside the barn. So we have two contradictions, and to demonstrate the essence of this contradiction, we can imagine trying to now shut the doors of this barn to trap the pole inside. Well, according to our picture on the left, so according to somebody in the barn, it seems like the door should be able to close and trap the pole inside, at least momentarily. Whereas according to Superman, because it's the barn that is length contracted, the doors of the barn shouldn't be able to close and contain the pole. So what's happening? Do the barn doors close or do they not close? So we seemingly have a contradiction. In one reference frame, the barn doors can close, and in another reference frame, they can't. So this is more than an optical illusion. This is this is a physical paradox we seem to have, in that the doors are a physical thing, so whether they can close or not is a question of what physically happens in the universe. So we seemingly have a contradiction, and this is known as the barn paradox. And what it seems to suggest, at least at first glance, is that, well, there must be a special reference frame, because somebody has to be right. Either the barn doors do close or they do not close. But of course, there being a special reference frame breaks the general principle of relativity that all initial frames are equally valid. And also it's not clear how we decide which reference frame is correct and what the person in the quote-unquote wrong reference frame would see. So we do seem to have a problem on our hands. The solution, it turns out, is to actually consider the Lorentz transformation matrix in its fullness. And doing that will actually solve this paradox. So that's what we're going to do on the next part of this video. So we've seen the paradox, the pole in the bar. You could also change it to the paradox of, can I fit my relativistic car in the garage? If cars move relativistically, we would have a very practical version of the paradox at hand. So this is an important paradox, in that we want to make vehicles that travel quickly, so potentially, we might one day generally have to worry about relativistic effects of fast travelling objects. But anyway, working with the bizarre mixture of sci-fi and agriculture that we were doing, where we had a pole and a barn, let's consider the solution to this paradox. So it turns out the solution is that whilst we took account of length contraction, as we properly should, we didn't take account of the full predictions of the Lorentz transform. Now, the Lorentz transform is a 2x2 matrix which mixes space and time components. And therefore, if we're going to think entirely about what will happen when a relativistic pole moves towards a barn and whether it will fit or not, we have to consider not only how space transforms between reference frames, but also how time transforms. Now, in previous videos, I think the 4th or 5th video in the playlist, something like that, we looked at the Lorentz transform and we derived the 2x2 matrix we have here, which mixes coordinates of a space-time event when going from one reference frame to another. Usually the primed represents the moving reference frame and the non-primed represents the stationary reference frame, but because here, in one reference frame the barn is stationary, in another reference frame the barn is moving, that distinction between primed and non-primed doesn't really help us. What is important is that primed is one reference frame and non-primed is another. So let's use this 2x2 Lorentz transformation matrix to solve this apparent paradox. Well, the first thing to note is that if we have two events that occur at the same location simultaneously, like let's imagine we had a very unhelpful barn which was infinitesimal, so the doors were practically at the same location, then from the perspective of somebody in the barn watching those doors close simultaneously, we could define the same space-time interval, we could define the same space-time coordinates to each of those barn doors closing, because they close at the same time, and they also close at practically the same location in space. And so, to make matters simple, I'm going to take the time that the barn doors are closing in this infinitesimal barn to be t equals 0, and they occur, and the barn doors are roughly at the same location, which I'm going to set to x equals 0. And I could do this for both these barn doors, and that's important. And I can do that for both these barn doors because they're practically at the same location in time and space. And when we put 0, 0 into our Lorentz transform, we get in the primed reference frame, so that same Superman's reference frame, we get, both doors close at t prime equals 0, and they close at position x prime equals 0. So in short, if two events are simultaneous and they occur at the same location in one reference frame, they always will in another inertial reference frame. Now here, to make matters simple, I've said the doors are closing at t equals 0 and the doors are positioned at x equals 0. You don't have to do that, but the important thing is, providing both doors are closing at the same location in space, if they close simultaneously in one reference frame, they will in another. However, in our situation, we have a pole trying to go into the barn. The pole in one reference frame is undergoing length contraction, so it's got to have some physical length, and therefore our barn's going to have some physical length. So the two barn doors are not in the same location, and that drastically changes the physics in terms of how universal we can be about the statement the doors close simultaneously. If we say, for example, that one one of the barn doors closing is a event in space-time with coordinates ct and x, where ct equals 0 and x equals 0, but the other barn door, well, it closes at the same time as the first one, in one reference frame, so in one reference frame we can still say ct 0, but this other barn door is displaced from the first barn door because our barn has some length to it. So we can't set the second barn door spatial location to be x equals 0 because that's where the first barn door is. So we set the second barn door spatial location to be delta x. So delta x you can think of as like the length of the barn. It's how far apart our doors are. Well, now if we take this new space-time event, the coordinates of this new space-time event, so the event of the second door closing, and we ask, what does this event look like for Superman? Well, Superman says, hey, CT prime isn't 0. So CT prime was 0 for the first barn door closing, but CT prime isn't 0 for this other barn door closing. And therefore the two barn doors in Superman's reference frame close at different times. And that's the key solution to the paradox. Because in Superman's reference frame, because the barn doors close at different times, the barn doors aren't trying to trap the pole inside the barn. We only have to have the pole being trapped if we're attempting to have both barn doors shut. But in Superman's reference frame, these barn doors do not shut simultaneously. There is a time delay. And it turns out, when one goes through the calculation, that this time delay actually allows for the pole never to be stuck within the barn in Superman's reference frame. So we have solved the paradox. And the solution is because there is a difference between reference frames on what happens simultaneously. From the perspective of somebody standing stationary relative to the barn, the barn doors close simultaneously. From Superman's reference frame, the barn doors do not close simultaneously. And this gets to some really deep philosophy, but before I emphasise this philosophy, it's worth seeing this visualised on a space-time diagram. So, a way to show certain features of Lorentz transformations is to draw a space-time diagram. So we draw an axis for time and an axis for space. And it turns out a good way to visualise the Lorentz transform is to think about the relative velocity between Superman and the barn as causing Superman's space-time axes to slant away from the space-time axes for the barn. And our dashed lines are lines perpendicular to our time axes, so events on the dashed line are simultaneous from the perspective of the axes that dashed line is perpendicular to. So for the barn, space, if we look at the barn's perspective, we have the two doors spatially apart. However, the barn doors close at the same time. And that was part of the setup of our paradox. We said, according to somebody within the barn, we shut the barn doors simultaneously and attempt to trap the pole in the barn. However, due to Superman's space-time axes being tilted, we can see that actually, these two events, the barn doors closing, are not simultaneous from Superman's reference frame. The barn doors don't close at the same time, they close at different times. So that's a good way to visualise the mathematics we have here. But to go back to some philosophy, the key thing is that because of relativity, even though we might be able to define what events are simultaneous within the given initial reference frame, those events, if they're spatially separated, will not be simultaneous if we jump to a different inertial reference frame which has some relative velocity. And what that means is we can't define universally what now is. We can only define now for a particular reference frame. Because if the present is the collection of events that are simultaneous, well, we can see from our space-time diagram or from our algebra with the Lorentz transform, we can see that what events are happening that are simultaneous depends on one's reference frame. So you might have heard the phrase the death of simultaneity, and the pole and barn paradox really gets to the heart of in what way simultaneity dies. It dies in the sense that there is no such thing as a universal now. What is now, i.e. what collection of events are simultaneously occurring, depends upon one's initial reference frame. Now, I think that's really cool, and I think that makes defining the present from a philosophical perspective very intriguing. But having talked about the mystery of time, let's move on to a paradox which is all based around time, and it's called the twin paradox. So, we talked about the pole and the barn paradox. Now we're going to move on to the twin paradox. Now, the twin paradox works with a couple of twins. Clearly, in this image we have non-identical twins. Works well either way. Well, if we do an experiment to prove this, we'll probably use identical twins because it'd be easier to tell the effects. But here we're working with non-identical twins. So we've got somebody who is on Earth, going about their daily business, perhaps visiting a few supermarkets, going on walks, whatever they get up to. And then we've got their twin sister, who is really adventurous and has a dream of travelling to the nearest star, Alpha Centauri. So she gets on a rocket ship and flies away. And then after visiting Alpha Centauri and greeting our nearby star, she then returns. When I say nearby, we're saying nearby in the context of space, but that is pretty far, at least as a plane or car goes. So by the time she gets back, a large amount of time has passed, even though she's been travelling really quickly. And a question is, when she returns, who is older? Is it the male twin or the female twin? And here we have in the apparent paradox, although the solution to the paradox is quite different to the last one, but in this paradox it has a similar setup to the last paradox we looked at. So in this paradox, we have who is older, whereas in the last paradox it essentially boiled down to what is shorter, the pole or the barn. So this paradox is kind of like the time dilation version of the pole and the barn paradox. So the paradoxes seem very similar. However, here the solution is quite different, because the paradoxes boil down to asking what events are simultaneous. The paradox seems at first much trickier to solve. And actually, special relativity doesn't really give us the answer. Because the situation seems fairly symmetrical, in that the person on the Earth can argue that, well, his twin sister is the one that is moving relativistically, so she should, from his perspective, appear to undergo time dilation. So she should come back older than he is. But equally, she could argue that no, she is stationary. It's the man in the Earth that has been moving. And so the man should have undergone time dilation, and so the man should be older than she is. Now, clearly, the female twin can't be both younger and older than the man, so we seemingly have a contradiction, we have a paradox. But the solution, it turns out, is to realise for this paradox to occur, the female twin needs to travel away from the Earth and then come back to the Earth. And for this to work, there's clearly a change in velocity, because the direction in which the female twin is moving changes at some point. And this change in velocity means that at some point the sister is undergoing acceleration. And acceleration breaks the symmetry. And when we're dealing with acceleration, then the female twin is, not in an inertial frame of reference, so in fact can't, generally when we're dealing with acceleration we can't use special relativity. If we're dealing with uniform acceleration we can, but since the sister is changing the direction of her motion, the acceleration might not be uniform. In fact, given how rockets tend to work, it probably won't be uniform acceleration. So we really need general relativity, at least to solve this in a general case where we don't make tons of assumptions about acceleration to force the acceleration to be uniform. We need general relativity to answer this question. And it turns out that when you take account of general relativity, it's the female twin who is actually the younger one. And you can kind of think of that as, acceleration, kind of like gravitational acceleration. So it's like the female twin is in some kind of gravitational well. The physics might be quite similar. And when you're in a gravitational well, time moves for you more slowly than for somebody outside of that gravitational well. So we might expect the female twin to be younger. However, it turns out that you can design other setups where actually the accelerating observer is actually older and not younger. But there's a bigger question mark around this paradox, which is why I call it poorly understood. In that, and it's debatable, it's worth saying, whether we do or do not understand this paradox. but it does seem like acceleration is breaking the symmetry. So acceleration is essentially is making time, if you like, less relative than it would be without acceleration. Acceleration is picking out a particular reference frame. A particular measurement of time is correct, very loosely speaking. And if we think that acceleration is the derivative of velocity, it's not clear why taking the derivative of something so relative as velocity should result in a quantity that has such non-relative impacts upon the physics. Why is acceleration having a more concrete and more discerning impact on time than velocity does? And this idea that acceleration has some absolute impact on time, unlike relative velocity, is something that Einstein during his later ages was slightly troubled by. And I personally, and this is just my personal view here, but I'm personally on board with Einstein on this, in that I don't think it's clear why, if we think of it physically and don't get lost in the mathematics, I don't think it's clear really why acceleration has such a objective impact on time in a way that relative velocity does not. So I think the solution to this paradox is mathematically well defined, but I think particularly when you take into account that acceleration doesn't always result in time moving slower, I think actually the solution to this paradox in a physical sense is not particularly well understood. And I think understanding the role of acceleration from a physical or philosophical perspective in physics, I think there's still work to be done on that. But now we've talked about two paradoxes, I'm going to finish this video by talking about why paradox is important. Why do we care about paradoxes? Because I've introduced two paradoxes, but then I've said that at least on mathematical grounds, we have solved both of them. And it's actually not too much effort to solve both of them. And in the general relativity playlist, I might at some point talk about mathematically solving the twin paradox. But given we have solutions, why talk about these paradoxes in the first place? So why do we have paradoxes? Why are paradoxes important? Well, I think the first thing to note is that paradoxes allow us to fit different pieces of physics together. When we were looking at the twin paradox, we saw that although special relativity doesn't really give an answer, due to time being so relative in special relativity, when we bring in general relativity, we do get an answer. So it shows us that in some cases, even when we don't explicitly mention aspects of physics that general relativity deals with, like acceleration, we have to keep in the back of our minds that general relativity might have something to say on the topic. When we were looking at the Barn paradox, I didn't mention it at the time, because with the space-time diagrams and the Lorentz transformation, there was a lot going on. But one interesting application of the Barn paradox is that, so, if we look at the perspective of somebody stationary relative to the barn, so where it's the pole that is moving relativistically, well, the pole would want to undergo length contraction. However, even from the perspective of the person inside the barn, the pole is still made up of material that will have some resistance to being length contracted. And what that means is if the pole moves relativistically, then any length contraction the pole tries to undergo will be perceived as the pole having a lot of tension from the perspective of somebody in the barn, because the pole is trying to contract or be much more contracted than it naturally would want to be. And so, the bonds are being squished between the physical material in this pole. And as the pole approaches the speed of light, the actual tension within this pole should become effectively infinite. And this leads to the idea that actually a pole moving relativistically due to the phenomenon of length contraction should appear to be under a great deal of tension. And this is an important idea in string theory, because in string theory particles are modelled as relativistic quantum mechanical strings, and the tension of these strings plays a huge role in their physics. And actually the point where generally we consider a string being relativistic is where the energy associated with its tension, ultimately due to length contraction, where this energy associated with tension is more than the energy associated with the string's rest mass. So the Barn paradox opens the door to a phenomenon which is important in string theory, which used to be quite a popular idea in the foundations of physics. Now it's less popular, but it's still worth considering and worth exploring. A lot of mathematical progress has been made. It's just string theory is now less popular than it used to be because we haven't found any direct or even firm indirect evidence of string theory. But we might one day. Cosmic strings are something that string theory discusses, and maybe we might one day find cosmic strings, and tension plays a very important role within the physics of cosmic strings. But anyway, paradoxes are important because they show how different bits of physics fit together. Paradoxes are also important because they really hone down what different terms mean that we use in physics and how universal we can be about those terms. So when we were looking at the Barn paradox, we saw that actually a major part of the solution is the realisation that there is no such thing as a universal now. So what we define to be the present is subjective. It depends on one's initial reference frame. Also, when we looked at the twin paradox, I mentioned a little bit about, acceleration having some objective nature on the passage of time being somewhat puzzling. The way that acceleration breaks symmetry in a way that relative velocity doesn't, even though acceleration is just the time derivative of velocity, both velocity and time are relative. But I think being precise with terms and understanding clearly in which context we can use them, and perhaps even more importantly, in which context we cannot use them, is a major part of allowing physics to develop and make good progress, because it means that we're working with a really solid ground, a very solid foundation. So I think paradoxes are important for the future growth of physics. And the last thing I would like to mention in terms of the importance of paradoxes is that paradoxes show us that there are always mysteries with the universe. Some of those mysteries we might be able to understand, like the lack of a universal now, even though understanding it doesn't stop it being mysterious, because it still feels quite magical, at least to me, and I think to other physicists as well. But equally, paradoxes try to solve certain hypothetical physical scenarios, certain potential mysteries, but in the process open up even more mysteries, like what is the nature of acceleration in relation to time. So I think paradoxes are a really rich source of inspiration for physics. So that's why I think paradoxes are important and important to study, even when we have the solution at hand. But this is the second to last video in the Special Relativity playlist, so I'd like to say thank you for everyone who's clicked on this video, had a look at it, or journeyed with me through the wonderful world of relativity. The next video, so the last video on the Special Relativity playlist, will be about neutrinos and neutrino oscillation. Both what it explains and, in the true spirit of this video, how that explanation leads to even more puzzles. So if you're interested in particle physics or relativity, hopefully that video will contain some core nuggets of physics in there. But anyway, I wish you a brilliant week ahead, and keep exploring the wonders of the universe.